I think I left off with, we talked about distillation, talked about making moonshine, that kind of thing. That was one way to separate things based upon their physical properties. When you know that things boil, for example, two things boil at a different temperature, you can utilize that because you know that to boil means that it turns it into a gas. So if you know and you can control that, and you have something that has a lower boiling point than something else, then you can crank it up to the boiling point of that substance, allow it to turn into a gas, leaving behind the other substance that is still in aqueous form. Then you can sort of, let that gas run through a condenser, something cold, and bring them back together, those molecules closer together, turn it back into a liquid. You can collect it and then redo that and purify it and that kind of thing. The proofs, of course, like with alcohol, something is 80 proof. The proof is actually twice the percentage of concentration of the ethanol present. So something that's 90 proof would be 45% ethanol. Okay. You'll also note that it's not possible to, alcohol in its natural form, you can't really get much past 95% alcohol. There's some chemistry reasons that we're not going to go into, but it's pretty much accepted that you can't get 100% alcohol. Okay. Filtration was another way to separate things. It shouldn't have to lecture on that too much. You should know how that works. Especially good for like separating solids from liquids and that kind of thing. If you look in the beginning of the lab manual, you will see explanation how to prepare filtration. It's more than just taking something and dumping something on something else. There's a certain way. If you have circular paper and you've got a funnel, how do you fold it? That kind of stuff. So I'm going to expect that if you ever need to use that, you'll read that on your own. Okay, I told you there's some things there at the beginning of the lab manual that you'll need to sort of just know. So you'll need to look through that before we run any labs. Okay, this brings us to what's called the conservation of mass. And what this means is sort of like the whole thing about matter and the fact that you cannot create or destroy chemical matter. We do not have the ability to do that. If something disappears, that's fine, but what you have not done is made it cease to exist. All that you have done is cause it to shift form and take the shape of something else or become tied up in a different type of chemical. A carbon atom, for example, if you have gasoline and you burn gasoline, you react a carbon-containing compound like octane with oxygen, you react them together, yes, that fuel will disappear. Octane, as you know it, may disappear. However, those same C's and H's that made up octane, all they've done is moved and become part of something else now. You've made carbon dioxide and water as a result of that. So nothing ever is made. You cannot create or destroy this matter. Okay? And as such, you should be able to account for it in all the reactions that you do. So we've got what is called the law of conservation of mass. Matter is neither created nor destroyed in a chemical reaction. So you can account for it. That means however much of stuff you had to start with, whatever is produced from mixing that together has to add up to the same amount. Okay? That doesn't mean what you're holding in your hand is going to be the same because, for example, if you mix two things together that are liquids, they may have a mass that you can weigh, and then when you mix them together, you're holding it and all of a sudden it weighs less. Why might it weigh less? What might have happened? Okay, into what state? Gas. What if it would form a gas and all that gas left? And now it's out there, but it's not necessarily in your reaction vessel, so you're not measuring anymore. But you can account for it. It was there. Okay, that's my point. You can account for all of this stuff. So on the left side of when you mix things together in a chemical equation, when you mix stuff together, those are called the reactants. Whatever comes about from mixing those together, and thus what is on the other side of the chemical equation are called products. Okay? So we mix together reactants to make products. So what we are saying is that whatever mass of all your reactants are should be the total mass of all of your products whenever you're done, because you cannot create or destroy matter. Okay, so take a look at this example. Let me close this here. They may not want to listen to my lecture in there. Okay. We went back to we talked about this butane lighter, okay, and what is happening there. Let's take this into consideration. Let's say that you have 58 grams of butane, and you are reacting it, burning it in 208 grams of oxygen. What you end up forming is 176 grams of carbon dioxide and 90 grams of water. Now, if you look, the butane reacting with the oxygen yields, that's how we would say that, okay? These reactants yield these products. What you will notice is if you add 58 and 208, and you add 176 and 90, you should get the same answer, 266 grams. Now, this carbon dioxide and water are actually in gaseous form. So what you would actually see is you would see that whenever these things burn, this just disappears and you're left with nothing because these gases have escaped and now they're out in the atmosphere. But you can account for them. They were present. All right, now shifting gears from matter to something else, because we said that matter was anything that has volume, anything that has mass, and that takes up space, or thus has volume. So anything that is, all the atoms, all the matter is made of all the atoms that exist. There is another thing that exists in our universe that is not matter. It does not have mass. It does not take up space. It has no volume. However, it is there. If you don't believe me, then you don't believe that your cell phone actually works. You don't believe that microwaves actually work, that you can listen to a radio. These all have radiation. They work off waves, okay? Energy waves. Energy has no mass and it has no volume, but it's there, and it certainly affects matter. It can come it can work on matter. It can cause matter to change its shape. UV radiation surely has energy associated with it. It can cause, we know that, there's a higher incidence rate of skin cancer with bombardment of UV rays. Why? Because well, in a very generic sense, UV rays have energy associated with them as they are moving, and that energy then can come in contact with matter. Matter can absorb that energy, and when things absorb energy, chemical reactions start to occur. Okay? All right, so here's energy. Things that do not have mass and volume. Basically, you have two things. You got matter and you got energy. It's going to be one or the other. Everything. It's anything that has the capacity to do work. Now, I'm not talking about work like, you have your own definition of work. In the sciences, work is defined a little bit differently. In physics, we would define it as the ability to move a force over a given distance. That is work. You can apply that to the same in chemistry, but the distance is going to be very, very small, atomic size kind of things. So energy is anything that has the ability to cause something to happen, the ability to do work. Like I said, all this matter is going to be directly affected by this. Okay? It'll cause physical changes. It'll cause chemical changes in this matter. For example, you know how like those tinted those tinted eyeglasses, that can turn dark in the presence of the sun? That's chemistry. What you have is UV radiation interacting with molecules that make up this film that's on these glasses, and those molecules are absorbing UV radiation and changing form. And when they change form, they reflect light differently to the point where they reflect much less light, or they reflect more light, absorb much less light, and less light travels through, and that's how come you can get that different shade in color. It's actually a chemical reaction with UV radiation. In the case of physical properties, if you have radiation coming from the sun and you have a glass of water inside versus outside where it can get bombarded by radiation, where's it going to evaporate faster? In the warm sun, right? This radiation is coming in. It's going to cause that physical change, liquid water moving into gaseous water much faster. So certainly energy plays in with matter. So like we have the law of conservation of mass, where matter can be neither created or destroyed, we also have a conservation of energy. You cannot create or destroy energy. Okay? At least we can. Maybe something that can, but we can't. So as such, we can, though, keep track of all the energy changes that occur. Whatever energy goes into something has to be accounted for in all the energy in which, whatever it turns into, whatever other forms and wherever this energy goes, you can account for it, and those numbers should be equal. It's kind of weird to think about that. But the total amount of energy in the universe is constant. The universe is a big place. And the laws, this is the best we have to work with. We've studied the laws on this planet. We've studied laws and how they sort of work the same on other planets, at least in our own solar system. And it seems that, for the most part, the laws of physics and chemistry apply. Now, what happens when we go light years away from here to another planet? Do the same laws of chemistry and physics apply? Well, probably, who knows? Maybe we'll never know. But all we can do is think inside the box that we have created for ourselves. This seems to explain things, and it seems that there's every indication that all of the energy in the entire universe is constant. So all it is doing is constantly changing forms. Think about, things when they die, from just a biological perspective. You decay, right? Things go away. Do you disappear? In a physical matter sort of way, no, you don't disappear. What happens is the atoms that make you up are redistributed. They are taken in by soils, by microbes, by all kinds of things, and the carbon atoms and the hydrogen atoms and the oxygen atoms that were once you have now moved all through into different places into the environment. And who knows where it ends up. That some of these carbons that are you, by the time certain microbes are degrading, and certain things eat those and certain things eat those, and who knows how far away one of your atoms can travel. I read a statistic one time. Just a mathematician came up with the math to show, I don't forget the number, but it was like he calculated the probability of you breathing an air molecule that like Beethoven or Mozart would have breathed. I forget which musician he picked. So everything is recycled. All of the atoms. Realize from a biological perspective, I'm not trying to include anything metaphysical or anything, just from this perspective, looking at the atoms, that's what you got. Okay? We are recycled in terms of our atoms. We're constantly flushing stuff out of us. You don't think atoms leave whenever that happens? Whether it's through our waste, our breathing, all of this was part of us at some time, and it's constantly moving throughout the universe, and it's always constant. It's just constantly shaping and changing its form. Kind of weird. Okay, wait till we get into quantum mechanics, and then you'll really challenge what you think reality is. All right. What did I say here? See, now we can move this, right? We can move energy from one place to another. When we have that sun, and like I said, it's 93 million miles away, but there's so much nuclear fusion that's happening and releasing so much heat. Okay, our sun's a big nuclear reactor up there. It's actually fusing hydrogen atoms together to make helium atoms, and it releases so much energy. When it does that, that energy is radiated out in all directions, and some of it comes towards us. And as it gets here, it certainly can change form. There's a very fundamental step in all of life that has to happen. Realize how important the sun is. Obviously, we can't live without it, right? But it's not just because of the warmth. It's also because of the fact that it's so big and its gravity holds everything in orbit. But not only that, it's the starting point of all of life on Earth, even in the food chain. Because you have autotrophs, you have photosynthetic organisms that rely upon the sun to help them position carbon atoms in such a way. The energy from the sun allows them to position carbon atoms in such a way that they can form sugars and then use it for energy. And if they can't do that, then we don't ultimately get to where we are in the food chain. We rely on those organisms to do that assimilation for us. We have changed the form. Anybody remember if you took any other like biology or A&P classes, what is the energy currency that we use in our body? What molecule gives us energy that we constantly use? ATP. We can take in glucose and that kind of stuff and then convert that into ATP. Guess what? All that ATP you can ultimately trace it back to. You can trace it back to the sun. You can trace it back to those original chemical equations. And we have converted it. The fact that we have ATP shows you the law of conservation of energy, this energy coming from all over the place, let's say the sun, for example, and we've converted it into a different form that now we house inside of ourselves to use for energy. Pretty crazy. All right. Matter does possess energy inherently within it. When a piece of matter possesses energy, it says, it can give some or all of that energy to another object. So it's just like hot potato, literally. I mean, you can do that. You can pass energy from one place to another. So all the chemical and physical changes that we've been referring to, those are all going to come about because of the matter changing energy. Energy is changed or exchanged between things. That's what's going to drive all of these things that we're going to witness. Okay, we've got two branches under which we can classify the types of energy that exist. Two big ones. Maybe you've heard of these before, maybe you haven't. But we have what's called kinetic energy and potential energy. What is the difference? Well, kinetic energy is going to be energy associated with movement or motion. Okay, for example, Anybody ever been to, what is it? Is it Spring Mill that they do they grind the corn and all that? You go there, you can see a great example of how these kinetic and potential energy sort of interplay with each other. That is a water-driven mill, right? The water comes in, it's got the little Ferris wheel type buckets, and that water in itself, before it hits that big wheel, let's say there's a moment in time where it's just sitting there before it falls. That water that's right there at the end of that trough before it falls in has potential energy. It has the potential to create work. Even though it's not right now, it can. Okay? Sort of like the water at the top of this dam. It's sitting there. It has the potential to, when it starts rushing past, distribute force to things and cause things to turn, right? When it's moving, it has kinetic energy. When it's just standing in a position, by virtue of its position, we say it has potential energy. So what happens is, for example, if I'm holding a ball, and I'm holding it right here, it's not moving. Well, theoretically it is, right? It's moving 1,000 miles an hour. But from my frame of reference, as I'm standing here, it appears to not be moving. So I'm going to say that it has 0 kinetic energy. However, it has a lot of potential energy. Here's what happens. As I drop that ball, it's going to start gaining kinetic energy. You see why? Its motion is increasing. And gravity is an acceleration. Okay? When you fall towards the earth, you continue to fall faster and faster and faster and faster until you hit the earth. So as this ball is falling, its amount of kinetic energy, because associated with motion, is increasing and increasing and increasing until it hits the ground. Now, right before it hits the ground, a theoretical point, what you have done is converted all of this potential energy into kinetic energy. Okay? You see what I mean? This potential energy is constantly decreasing. The amount of potential, the higher I go, the more potential energy I have. As I drop it, my amount of potential energy is constantly decreasing. My amount of kinetic energy is constantly increasing, and they are sort of switching places. Okay? So potential energy is energy because of position, because of where something is located and how it's organized. When that goes into motion, you have kinetic energy. Okay? ATP, for example. ATP is potential energy. The only time you get energy out of that is when that phosphate bond is broken. When that last phosphate bond is broken, it releases energy. Now you can have a release of kinetic energy. Locked up in that bond, it was potential energy. It had the potential to release that energy, potential to create work. Okay, so it's stored energy. Potential is stored energy. All right. We're going to measure energy. We're going to do that in our 1, 2, 3rd lab, I believe. You'll be able to measure energy changes in a system. You've probably seen this before, right? A calorie. A calorie is a unit, just like centimeters measures length. Calorie is a way to measure energy. Okay? By definition, what a calorie is the amount of energy that you would need to take 1 gram of water and change its temperature by 1 degree Celsius. However much energy that is, that's what we define as a calorie. Okay? So a calorie is how much energy it would take to raise 1 gram of water 1 degree Celsius in temperature. Somebody over there? Okay, now I'm about ready to depress you if you've gone on a diet or anything like that. A kilocalorie. Kilo means what? 1,000. A kilocalorie is 1,000 calories. So in other words, a kilocalorie is the energy that would be needed to raise 1,000 grams of water 1 degree Celsius. Makes sense. However, what's depressing is food calories are actually kilocalories. Okay? When you look at something and you're drinking a pop and it says 120 calories, those are food calories. Those are 120 kilocalories. That's actually 120,000 calories. Okay? So that'll change some things now, right? Well, it's actually they've covered themselves because notice how the C should be spelled with a capital C, right? You'll see calories with a capital C. You'll see calorie with a lowercase c. It's implied in food chemistry that calorie with a capital C is a kilocalorie. So technically, by law, they haven't lied. Do what?
Why don't you just know that?
Yeah, that's right. They should just assume that you know that. This cal. Yes. This one. A kilocalorie is the same as a calorie with a big C. Yes. Now, however, realize that your diet is organized around food calories. So if someone says 2,000 calories, they're talking about 2,000 food calories. Okay? So it's not like they're trying to trick you and make you, eat 1,000 times more than what you normally would or anything like that. So the diets that you get recommended they take that into consideration. But just so you know the truth, it's actually 1,000 times more than that. Okay? So when something has 180, think about this. Now what's in that pop right there? What, 120, 180 calories? What's that got? Oh, it's diet. It's diet. It's diet. That Pepsi there, what do we got? How many calories in that? 180, 120, 210? What? Just 100? Okay. So the whole pop, how many calories in that whole pop? 250. 250 calories. That means 250,000 calories. There's enough energy in the bonds that make up that pop right there to raise 250,000 grams of water 1 degree Celsius in temperature. Okay. That's a lot. It seems like a lot, but you also got to realize that there's a whole lot of energy in our body that is broken and released all over the place. So we use that much energy. If at any point in our body that all of the chemical reactions that were occurring, if they ever happened at the exact same time and energy was released at the same time, we would just vaporize. Okay? I know somebody was going to ask me about spontaneous combustion. Of course, there's no evidence because it's gone. If it ever actually happened, there's no evidence, and all you have then is like someone saying that they saw it or whatever. So there's been no scientifically controlled experiments to illustrate spontaneous combustion because, first of all, I mean, you would have to have, astrologically speaking, all the planets would have to align just the right way to ever make that happen again. So there's no proof. Okay? However, if you sat there and saw somebody spontaneously combust, you may not need me to say that there's proof. That might be proof good enough for you. I'm pretty sure I'd tell the world, but they'd think I'm crazy. They already do anyway. So, all right. Some of the units we're talking about with energy, you'll see calories, but you'll also see joules. Okay, joules is another way to measure energy. Here's your conversion factor. These two things are equal. 1 calorie is equal to 4.184 joules. So that'll be a conversion that you'll need. Already said this one, right? 1,000 calories is actually a calorie with a big C. So that's the same thing as a kilocalorie. Keep that in mind. A kilowatt hour, this is what your electrical meter, when you go outside and you can see it turning and stuff like that, the guys when they come read it, you're actually measuring energy in terms of kilowatt hours. How many, in a watt, well, we can get it in physics, we can go into that, but it's like 746 horsepower to a watt, or 1 horsepower, 760, I don't remember. There's a conversion there. But the units go all over the place. But a kilowatt hour is what they would measure, okay? Because it doesn't pay off to measure joules because joules are so small and we use so much more than that. A kilowatt hour, over here, is 3.6 times 10 to the 6th. So about 3,600,000 joules for every 1 kilowatt hour. You can look on your electrical bill next time and see how many kilowatt hours you're using, and then you can convert that to joules just for fun. Okay, converting energy units. Okay, come on, you want to be a dork. Everyone's a dork at heart. I've decided. Everybody's a dork at heart. They just don't want to let it all out. That's all it is. Because they're afraid. There's going to come a point though when you don't care anymore. And when you're young like me and you recognize that early, then life's just so much easier, man. I'm telling you. All right. Here we go. A candy bar contains 225 calories of nutritional energy. How many joules would that be? Here's what we know. We know we have 225 calories. Can we go straight from calories to joules? Yes or no? Let's go back one. Okay, we can go from this calorie to joules, but we can't go from big calorie to joules. But what can we do? Yeah, that was perfect. Did you hear everybody here? You can go from big calories to little calories to joules. Okay? All right, so let's do that. Let's do it. Here we go. There's the conversions that you need. You already told us that. So create a solution map. Where are you going to go? You told me you're going to go from big calories to little calories to joules. Now, what conversion factors, how would you position those in order to achieve your result. You know this to be true, so you would position it like this so that these would cancel out. You know this to be true, so these now would cancel out, and you're left with an answer in joules. Okay? So you'd multiply everything across the top divided by everything across the bottom. Now, what may help you when you're solving these problems, if you're not good at keeping track of all this stuff, remember this is the same thing as over 1, right? So you can think of this as a numerator, if you'd like. When we get into bigger numbers, especially when there's a lot of stuff on the bottom, these are 1, so that makes it easy. You don't have to worry about them. But when we get decimal numbers and stuff like that on top and bottom later on in the semester, you may want to just multiply everything on top, write down, keeping track of sig figs and that kind of thing, write down a number for the numerator, then multiply everything on bottom, write down a number for the denominator, and then do one step at the end. That way you don't get confused. Now, if you don't need to do that, then don't. But if that helps you, then do it that way. So our answer is 941,400. But notice we are limited to, here's what we were given. This is a measurement value, 225. These are all definitions. Okay? So we have to limit it to 1, 2, 3 significant figures in our answer. That's why I cut this off here. So it would be 9.41 times 10 to the 5th. Okay? You would have to round this down. So this will be like 941. Then you have to take everything down after that to like zeros. Okay? So 941,000 was how you would round that. That would be 9.41 times 10 to the 5th joules. Okay? Because you put your decimal here, 1, 2, 3, 4, 5. We had to go all the way over there. Does it make sense? Well, which is bigger? Joules are a lot smaller than calories with the big C, so you should have a whole lot more of them than what you have of calories. So it makes sense. Okay, what is heat? Heat and temperature, are they the same thing? If you increase the heat of something, do you increase the temperature? If you increase the temperature, do you increase the heat? If that is true, does that mean they are the same thing? Okay. They're not, technically. Heat is when energy moves, and we can see it and feel it and record it. Heat is the movement of energy between matter. Okay. If there's energy associated with this piece of matter, and we can see that it is transferred to another piece of matter, we call that heat. Now that's a little bit different probably than what you imagine heat is. But it certainly applies to what you think heat is. If you think about it, it's sort of the same application. Temperature is not necessarily heat. They are related. Temperature, what it measures is the average kinetic energy of your sample. So if you have the temperature of water, what you are measuring is the average kinetic energy, in other words, the energy associated with the motion of water in that sample. How do you think you can increase the movement of water? What can you do to it? Heat it up. When you heat it up, you transfer heat from one matter into, or from energy or from something into that water, from a flame, from a Bunsen burner, whatever, into that water. You've increased its heat because you've increased the amount of energy you are moving from one place to another. What happens as a result? The average kinetic energy increases, and you measure that with temperature. So you can see that temperature and heat are not the same thing. And temperature is not necessarily a measure of heat. It's a measure of the average kinetic energy. Because consider this. Let me ask you. Which has a greater temperature? A 90 degrees Celsius cup of coffee or a 40 degrees Celsius bathtub filled with water? Which has a higher temperature? Okay. The bathtub, you said. Temperature. How do you take the temperature of something? Stick a thermometer in it. So stick a thermometer in those two things. Which one has the higher temperature? Okay, the coffee. You thought I was trying to trick you, right? And I'm going to with this one. The temperature of those two situations, 90 degrees is a higher temperature than 40 degrees, right? There's a little bit of coffee, there's a whole lot of water. If I asked you how much thermal energy, in other words, how much heat could you find in the coffee cup versus in the bathtub, you would actually have more heat that could leave that bathtub than you could in that cup of coffee. There was more thermal energy associated with that bathtub. Why? Because there's more water, there's going to be more molecules moving around with that energy. Okay? That's the difference. There's a difference between temperature and heat. Okay? All right. Heat is like particles in a sense that it will go from a place where there's a lot to the place where there's less. If you have diffusion, you know that if I have a whole bunch of something here and I let go of it and let it go, it's all going to spread out and it will go to a place where there's less of it. We know this. Energy is the same way. Heat is the same way. If you don't believe me, get a piece of iron, let it set in the fire for a really long time, and then grab it. What happens? The energy leaves from that piece of iron and goes directly to your skin. That is energy moving. It's heat energy going from one matter to another kind of matter. Okay? So it flows. It goes from a place, you don't burn that iron burns you. It goes from a place where there's more heat to a place where there's less heat. Until they reach the same temperature. It's like a hot cup of coffee, right? What's going to happen? You hear, this happens, see, you'll see that this stuff happens around you all the time. That's what I want you to see is when we study this kind of stuff, what we are doing is looking at things that already happen all around us and you've never really taken a notice of. Like a cup of coffee. What is happening to it? It's sitting down there and it has a higher level of thermal energy associated with it, heat energy associated with it than does the immediate surroundings. So what does it do? It gives off that heat energy and it leaves, it radiates out into the environment until eventually that cup of coffee reaches what temperature? Room temperature. You come into an equilibrium, a balance. Okay? Once you get to that point, stuff isn't really, it's a hot cup of coffee in a cold room. What you need to understand, and this is what freaks people out too, there's no such thing as cold moving. There's not. There's heat moving, or lack of heat in a situation. I'll explain this further a little bit later, but for example, I remember my mom, whenever you're younger, right, or my dad especially, if I'm standing in the summertime, the air conditioner's on, and I'll open the door and I'll stand there and he'll say, "Hey, you're letting all the cold air out, right? All the cold air's leaving." No, it's not. There is no such thing as cold air that's leaving anywhere. What you have is the hot air coming in. Stand in the doorway. Find a window. If you have an old house that might leak a little bit, or a doorway that's got like where the door shuts, there might be a little bit of a breeze coming in. Light a match, okay, and see which way the flame goes. Is the flame going outward or is it coming in? You feel cold, but what actually is happening is the warmer air is going to diffuse away towards the colder region. All cold is the absence of warmth. Okay, so cold air is not going to be. I'll explain this later, and I'll explain to you why, how freezers and refrigerators and how all that applies. People don't buy it. My mother-in-law, anytime you try to explain anything like this, she just calls it monkey stuff. It's you and your monkey stuff, I don't know, but it, huh? That's kind of how I feel about it too. Well, but I mean, it's certainly once you can learn about what's going on, you can start, seeing things happen with a whole new perspective. And you can start understanding, and you can see where all these advances have been made and the things that we have, we normally wouldn't have unless someone sat down and made these keen observations about what was going on in our environment. So to you, it may not directly apply to your life, but it does. You're not the one sitting down thinking about it, but guess what? There's a whole lot of people out there who are, and that's why you have things like cell phones and books and papers and automobiles and all this kind of stuff. Okay? Keep in mind, the unexamined life is not worth living. All right. I already talked about what temperature was, so we can go through this. What is important to keep in mind is that when you have a sample of molecules, realize that just like us at any given day, right now I'm feeling pretty good. I got a lot of energy. Chemistry excites me. If it's a bad day and I know I'm getting ready to give a chem lecture, then I get picked up for it. So it's good. It's what it does. It's my drug. Some of you don't feel that way at all. Okay? Some of you think it's a drug, but it's more of a sleep aid than anything else. Now, just like in this room, there are different levels of energy. In a sample with a bunch of molecules, each one of them probably at any given time is going to have a little bit different amount of energy associated with them, right? Now, we can take an average of our energy and how we feel. We could rank it like 1 to 10 or whatever. we could get an average and say, as an average, this group has an energy level of about a 6, 0.6. Okay? Temperature is sort of the same way. What you got to remember is when you take the temperature of a sample, you're taking the average. There's going to be some molecules in that sample that are much higher than that, have a whole lot of energy. There's going to be some that are very almost lethargic. They have very little energy. Okay? So keep that in mind when you have a sample. Here's some common temperature scales that we'll use. Don't even worry about this last one. You'll never come across that in your studies probably. But these three are very important. Celsius, Kelvin, and Fahrenheit. Now we use Fahrenheit regularly. Lucky I got that word out. I never can say it. Celsius is becoming more common. Like I said, usually if you observe the metric system, you observe the centigrade scale or the Celsius scale, and we don't like to do that. However, it's much easier if we ever just go along with that. You will do all your temperature measurements in this class in Celsius. Okay? See how they sort of rank. If you look, one thing about Fahrenheit and Celsius, you'll notice that as low as they go, okay, we're going to say it's negative 452 degrees Fahrenheit, negative 269 degrees, sorry, negative 273 degrees Celsius. Now, you'll see that the scales between Celsius and Fahrenheit have different steps. The degree from one degree to the next, there's a bigger gap between these two guys. However, what I want you to notice about this is this Kelvin scale. Notice it never goes negative. And I'll explain a little bit later how sort of the theory that went into this and how it came about. But using a Kelvin scale allows us to never have a negative value for temperature, which is going to help us when it comes to math. This 0 Kelvin is what we call absolute zero. It is the theoretical point at which all matter stops moving, motion ceases, and basically matter ceases to interact with any other matter. At all point, things would cease to exist. Yeah. Not in natural situations, no. Have we ever achieved absolute zero in the laboratory setting? No, but we're getting closer and closer and closer. I'll explain all of that later. Okay? I'll explain it all later. Right now, I need to explain some other things that go into that, and that'll be in an upcoming lecture. I'll explain all of that. I'll explain how, on this first lab that you do, we're going to talk about what's called interpolation and extrapolation of data with your graphs. Predicting values. Going beyond the data that you measured and predicting based upon the equation that you generate for your line. Or looking at something that you didn't directly measure, a certain point that you didn't measure on your data, but falls on your line that you can predict what it would have been had you had measured it. When you get to things like that, you can start predicting things like this, that this would exist, and that everything would converge on one point and everything would cease to work at that point. I'll explain it later, since it's beyond what we're doing right now. But what's important for you to grasp right now is that there's no values less than zero. There's no negative values. When we get into dealing with gases especially, we have a whole chapter about how we deal with gases. You'll have to use this Kelvin temperature scale to keep these negative values from appearing. Okay. All right. We can convert, obviously, between them. So there's an equation. I will obviously not require you to memorize that. If I have you convert anything, your equations will be provided. But just know how to plug things in. You know, whatever you're missing. If you're given Celsius, realize you've got to solve for Fahrenheit. You have to rearrange this algebraically to solve for the missing variable. If you're given Fahrenheit, it's, according to this equation, it's pretty easy. You can just plug that in and solve for Celsius. So be able to do that. Be able to convert back and forth. Some of you even have a calculator that does it for you. There's probably a Celsius Fahrenheit button on there. A Celsius degree is actually about 1.8 times bigger than a Fahrenheit degree, so it covers a bigger gap. Like, for example, the boiling point of water is what in Fahrenheit, you know? 212 degrees Fahrenheit, and what is it Celsius? 100. So you can see that 212 is a bigger gap than 100. So the scale is actually a little bit bigger. So whenever you say, it says the standard used for 0 degrees on the Fahrenheit scale is a lower temperature than the standard used for 0 on the Celsius scale. In other words, all you need to get out of this is that they're not the same. You got to convert between them. There's a bigger difference between the gaps on the numbers. Okay. Now the Kelvin, what's nice is that, like I said, negative is done away with. We have all positive values. Okay. And what's nice about this and dealing with this is we don't have to reason things out in our mind, because we know that if something changes, for example, if I stood right here and I took 5 steps, or say I walked 5 meters that direction, that I walk a negative 5 meters. Does it make sense to say that I walked a negative 5 meters? No. Whenever you measure things, like if you measure how much something is, there's no negative signs associated with that. Now, in physics, we might say, we're going to say this is positive and this is negative. So if I walk 5 meters in that direction, I will say that I walked a positive 5 meters. If I walk that way, I'd say I walk a negative. But that's only because I decided that's what it was. I just made that up in my problem. In real life, if you go 55 miles an hour and you slam it in reverse and you go 55 miles an hour in reverse, you're still going 55 miles an hour, right? So that's why Kelvin becomes important. We don't have to deal with any negative signs when we do all of that. Okay. Now, at absolute zero, it's too cold for matter to exist because, like I said, all molecular motion would stop. That occurs at 0 degrees Kelvin, which would occur at negative 273 degrees Celsius, which would occur at negative 459 degrees Fahrenheit. However, here's what's going to be very useful to you, for you to know. You know how I said that Celsius and Fahrenheit, the distance between numbers is bigger, like on Fahrenheit, it's a bigger gap? Not with Celsius and Kelvin. They're the same. So when you go up 1 on Celsius, you go up 1 by that same amount with Kelvin. So if you change 2 degrees Celsius, you've changed 2 degrees Kelvin. That's nice. So see if you can reason this through. If that is true, and that a Kelvin jump is equal to a Celsius jump, how do you think you convert between Celsius and Kelvin? Which is 273. That's right. To convert from Celsius to Kelvin, you add 273. To go from Kelvin to Celsius, you subtract 273. It's that simple. Okay? So there you go. This takes us to what we call specific heat capacity. All right. If I had a container of water, say this big, about like that, and I set it out in the sun, and I had a container of air, the same size, and I had a thermometer in each one of them, and I set them both out in the sun, which one do you think would heat up faster? Good. The air would heat up faster. Anybody even want to come up with a reason as to why? Could be. I don't expect you necessarily to know the answer to this question. I was just seeing. Huh? I don't know, maybe. I mean, that could have something to do with it. What? And you know this is true as well. If you have a swimming pool in here, right? For those of you, or if you know someone who does or been to one, you know for a fact that water takes a little while to heat up, and it takes a little while to cool down compared to other things like air, for example. You have one nice warm day, you're waiting, you got the pool open, and everything's clear, and you've got it clean, and you're waiting for the warmth to come in. Just because you have one day at 95 degrees doesn't mean the next day you're going to be able to jump in that pool. It may take a few days like that. And likewise, in the other situation, it's looking nice, and you get a cold spell, and you have one cold day. It drops down, well, in the summertime, say it's 50 degrees. It drops down because, we're destroying our world with global warming. And that happens. Is the next day, is the water going to have dropped significantly in terms of its temperature? No. It's going to hold it pretty well. Water has what is called a high specific heat capacity. In other words, it means it can absorb a lot of energy before it releases anything, before it warms up or cools down. Okay? If you want to heat it up, it'll actually absorb a lot of energy before you see any evidence of it heating up. Does that make sense? And likewise, if you're trying to cool it down, it's going to hold on to that energy longer than most things before it starts to cool down. Okay? It's sort of like it takes it a while to cool up, to heat up and cool down. If something has a very low specific heat capacity, the opposite is true. It heats up very, very quickly, and it cools down very, very quickly. Sort of like aluminum. Aluminum, if you can grab like aluminum, if you're baking a potato or whatever, at first it's hot, but it's hot because it's wrapped in the potato. I don't know if you've ever done this, but you could put aluminum in an oven, get it hot, bake it like you would the potato, pull it out, and within no time at all, you can grab onto that aluminum. Aluminum has a very low specific heat capacity. Okay, so specific heat is going to be the amount of energy required to raise the temperature of 1 gram of a substance by 1 Celsius degree. Okay, so how much energy would it take if you had 1 gram of this to increase the temperature of that 1 gram by 1 degrees? However much energy that takes, we call that the specific heat of that. It's a specific property. It's very unique. Everything has a different specific heat because everything is made of different types of bonds, okay, different types of and proportions of atoms. So like I said, the larger that specific heat is, the more energy it's going to take to raise a given amount, raise the temperature of a given amount of that object. Like density, remember density is what we call an intrinsic property. Density does not change with the size of the object that you are measuring. The density for something is always constant because what is density? It's a ratio of what to what? Mass to volume. That's right. So the bigger the mass gets, the volume increases proportionally. So that means that ratio remains the same. You'll find out that that's also going to be true for specific heat capacity. Okay, it's going to work the same way. It doesn't matter how much of it you have, it's still going to have the same specific heat capacity. Now we can actually use this to identify the type of matter. For example, in the lab that you're going to run, I'm going to give you an unknown metal. You're going to run an experiment on it, calculate the specific heat of that metal. I'm going to give you a table from which to choose, and you have to identify what your metal is. Okay, so you're doing a little unknown verification kind of thing. See if you can figure it out. Also, keep this in mind. This will be important whenever we are doing this exact same lab. The amount of heat that is gained or lost by an object depends on 3 factors: how much there is, what the material is, and how much the temperature changed. What this means to you is a mathematical equation that's pretty easy to work with, and I'll show you. Also, let me preface this by saying, if I have a glass of water, okay, and it is at room temperature, and I have a piping hot piece of copper, and I drop it in there, and I seal that cup back up, and the temperature of the water increases, assuming everything is sealed off and I don't lose any heat, what can I assume about that temperature increase in water? It's the same as what? Yes, I didn't hear what was said over here, but it was how much heat the copper gave off should be equal to the amount of heat that the water gained. Do you see why? Okay, keep that in mind. So, relating these 3 factors, how can we come up with an equation for specific heat? The amount of heat is going to be a factor of the mass, the specific heat capacity for that object, and the total temperature change that you observe. In other words, this. Okay? Q equals mc delta T. Q means amount of energy. It could be in calories or joules. Depends on what this is given in. If this is given in something that involves calories, your answer over here is going to be in calories. If this is given in something that involves joules, this heat energy will be in joules. It just depends. You'll see what I mean as I work through these problems. So Q is heat energy. M is mass. So like grams, kilograms, that kind of thing. Specific heat capacity. The actual measurement, like how much energy is required for 1 gram to raise 1 degree Celsius. There's an actual number there. You can look that up on a table. Okay? That goes there. And then whatever temperature change you measure. If you started at 25 degrees, you mix these things together, and it went to 31, you've got a 6 degrees temperature change. That's what you would put in there. Okay? Let's look at a problem. Relating heat energy to a temperature change. Gallium. This is kind of neat. Gallium is a metal at room temperature, about what we're feeling right now. This is about 298 Kelvin. About 25 degrees Celsius is what you're feeling right now. Gallium is a solid metal at room temperature, but it melts at 29.9 degrees Celsius. So if we increase it by about 5 degrees in here, and we had gallium, we would see gallium metal melt. Okay? If you hold gallium in your hand, it melts from your body heat. You're actually giving body heat off. It's moving from your body into that piece of gallium, and it will melt in your hand. How much heat? Let's quantify that. We can say that heat goes from one place to another, but what we've got to be able to do is tell me how much heat. How much heat went from one place to another? How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 degrees Celsius up to this 29.9 degrees Celsius? So imagine what's happening. You're holding a piece of gallium in your hand. You know that through your body heat, you can melt it. You know that when it starts to melt, the temperature must be 29.9 degrees Celsius at that point, because that is the melting point, it says, of gallium. So between that time when you're holding it in your hand and you wrap it up and it starts to melt, in that time, how much energy is being shifted from your body into that piece of metal? That's what you're calculating here. Okay? So what we need to know, first of all, is how big is that piece of metal? Because the bigger it is, the more energy you're going to have to put into it. The smaller it is, the less energy you have to put into it. So that's why this 2.5 grams becomes very important. We know how much of it's there. We know that when it starts to melt, this had to have been the temperature. So we know what our temperature change must have been from that to that, about 4.9 degrees. And I know that other research in other labs have shown what the specific heat capacity already is. That's nice. We can look it up on a table. It's been shown that the heat capacity of gallium is 0.372 joules for every grams times degrees Celsius. Okay? So how does this help us? Here's what we know. We know this mass, we know the starting temp, we know the final temp, and we know the specific heat capacity. We're going to be using the equation Q equals mc delta T, plugging those things in. We're solving for Q. So if we know that's true, we're multiplying these three things together. We can certainly go straight from these three values to Q based upon our equation. Let's plug in our numbers. Q equals 2.5 grams, which is our mass. That came from our problem right here, 2.5 grams, times C, which is the specific heat capacity, which is 0.372. Notice, see that joules right there? Notice these units. The reason they're like this is so that they cancel out. Okay? What's the last thing? Delta T. What was your change in temperature? It was 29.9 minus 25, which was 4.9, right? If that's the case, you multiply all those together. This would be, you'd change that to 4.9, multiply that, times that, and you would get 4.557. Okay? Now, when you subtract these two, you're limited to one decimal place with significant figures, so you got to write that as 4.9. So down here, we've got 2, we've got 3, we've got 2. Our answer is going to be rounded off where you see there, so it's going to have to be 4.6 joules. Why is it joules? Because they give it to you in joules to the point where that's the only thing that's left in your equation. If you keep track of your units, you'll see that you won't get them wrong because you can cancel out. The grams cancel out, the degrees Celsius cancel out, joules is the only thing left. Okay? Now, sometimes you may see specific heat capacity in calories per grams times degrees Celsius or something like that. Just realize then your answer would be in calories when you're done. It just depends on how this is given to you. Just keep track of your units and it shouldn't be a problem. Okay. All right. Done with chapter 3. But we can't quit. We've got to start in with chapter 4.